if you look carefully at the graph and the two tangent lines I've drawn, you should note that they are also inverses of each other, just like the function, right, the original two curves, the function and its inverse. Because you could, again, construct points on one, map them across a perpendicular line to y equals x, and land equidistantly, right? That's the same distance as this, on the other side, on the green tangent. So therefore, that implies that the red tangent and the green tangent are themselves inverse functions of each other. Okay? And the slopes of linear functions, right, or slopes of lines, that are inverses of each other are reciprocals. Slopes are the slopes are reciprocals. So therefore, that means slope of red tangent is the reciprocal of the slope of the green, and vice versa. So slope of red must be the reciprocal of slope of green. Okay, so now using the notation for these two, we have that slope of red, which is f prime of a, must be equal to the reciprocal of slope of green. That would mean 1 over. There's the reciprocal of this derivative, of this slope. So that's f inverse prime at f of a. Okay, so what do we have? Well, we really want f inverse prime at a, right? And we have instead an expression for f prime of a. But calling one by f and the other one by f inverse is really an arbitrary choice. So therefore, I can actually replace f here with f inverse and f inverse with f, because which one I call the inverse really doesn't make a difference. They're inverses of each other. So I can replace f with f inverse. So now instead of being f prime, it's f inverse prime at a equals 1 over, instead of f inverse, I have f prime, and instead of f here, I have f inverse at a. Okay, so there is the formula we've been looking for, you might say, derived from this picture. We now have an expression for the derivative of the inverse function at a location, and in terms of the original function's derivative evaluated at a certain location.